I've also learned from experts of data simulation that they actually have similar impressions as the. So I'd like to list down some of these impressions, and I hope when I go through all of the slides that you get that there is actually some reasoning behind why am I bad. So first of all, a data simulation person is a computing hog. It takes a lot of computing power. So every time I run my simulation, Mike Luthel or sysadmin will look at it because it may actually crash. And there's a potential chance, or there's a high chance that it will crash. So we have a lot of computing, we need a lot of computing power. I've got this comment last month when I was talking about data simulation. He said, oh, you're the one who abuses the data. He was actually a data person. So yes, in a way, we abuse the data. In a way, oops, sorry. There's no, in a way, we think the model is wrong, but we blame the data anyway. The reason behind it is that we don't really know how to correct the model. It's a very hard problem. The data is easy to actually change in the model or in a simulation world.
Okay, you can get the pointer to the bottom one.
This one?
The bottom, no, on the back. There you go, underneath.
All right. But my mentor on this data simulation also told me that we have a constitutional right to change the model or the data, but we are very conservative. And if you if you look at this analysis, reanalysis or forecast or analysis of operational centers, they are very, very conservative. They throw out a lot of data, okay, including GPS. And so they like satellite data. They will have that, but even the satellite data, they throw out a lot because they don't want the model to be cranking all the time. The other thing is we must do everything right, and that's a big expectation from us. That there's a lot of details, especially the small details in the model, in the observations that we need to understand to actually incorporate that as an information and translate that information to a better forecast, better analysis. All right. So think about a thermostat in your room or in your house. I like this because I want to buy actually this one. This is kind of a learning thermostat wherein the thermostat actually learns your behavior. And apparently there's a lot of reviews out there about this that says it doesn't really work because it doesn't know your behavior well. It cranks up a lot of your temperature to about 90 degrees or 78 degrees, I think. So they don't like that. But the good thing about this is that it actually increases or changes your temperature in a way that's very gradual. And that's what the simulation would like to do. Very small steps, very incremental steps so that the model won't crash. We don't like to have a big step, like a PID controller if you're an engineer. It has to have that, or else the factory will shut down. All right. So, as I told you, data simulation is essentially the combination of a model, a dynamic model, and an observation. And the goal, all right. And the goal really is to get a better estimate of the system, whatever system you want to look at. If it's a state or a parameter or a source, it's something to do with the system. And this is a physical system that we're looking at. Of course, it's in a North American monsoon region. So what I have here is an observation, a global model, a regional model. This feeds this as a boundary condition, an initial condition. In some cases, and a new model now, model prediction for different scales or something across scales, MPAS, actually had just one big model, and it zooms into a higher resolution. But the idea is that this simulation is just a wrapper of the information of the observations, and plus the model. And so, in our case, we estimate the atmospheric states of NAM, specifically moisture. This is our goal, as Yolande and Chris and Jamie already talked about. What we use is we're going to assimilate TPW or PWB, depending on who you talk to. Our model will be WRF, as Jamie have already pointed out. Our initial condition and boundary conditions comes from GFS or NAM. And our simulation is an ensemble common filter called DART. It's a community package for students who would like to understand this. There's a MATLAB code to actually play around with this. All right. Before I start, I'd like to have some toy example of what exactly am I talking about combination of information. Say, for example, we want to estimate the room temperature of this room, And we have two pieces of information, one from a guess from Dave Adams, and the other one from, let's say, Enrique measures gets a thermometer from Walmart, and then this measure temperature here. Okay, and both of this have obviously a relative. They have their confidence. They have their errors in it. So the idea is just to combine both to get a better estimate, right? And the first thing you need to look at is just the combination of this, weighted by W1 and W2, and say, okay, let's just take the average of what Dave and Enrique told us. So an average would be W1 and W2 will be 1/2, right? But that's not the case because we have a confidence, level of confidence of each of those information. And so we can look at this as our estimate is just our prior guess plus some increment, where our W2 will be calculated based on our level of confidence. That's essentially what it does. Maybe there's 3-4 lectures of this, but I'm just going to skip this. And essentially, what you do is just to minimize the square error of your estimate with the true value. You don't know the true value. We can talk about it later, but that's how you do it. And so what you end up with is a combination of information, where information is actually the inverse of the errors, the error variance. Okay. And so now we have an analysis. Oh, can I do that? So we have an analysis that is from our first guess plus some increment, which the increment is essentially the weighted average of the errors. That's it. That's it. What you want to know. That's data simulation. That's the least squares problem. There's two variations of this. One is two flavors of this. The variational method, wherein you think about this as a cost function, wherein you have a guess and an observation called y in this state. And then you kind of find the cost function. You want to minimize this first guess and find x such that the first guess is close to that within the level of confidence you have. And then you want also to minimize, you find x such that it's closely matched with your observation. Okay? And so what you end up having is the two Sorry. How many times? Okay. All right. So you end up with two cost functions that you want to minimize. And the solution to this is minimizing the whole cost function. And what you end up with is XA, your analysis. That is the minimum cost, the minimum variance, the minimum error you have. That's your estimate, right? The other way to do it, by the way, they call it forecast, they call it observations, and they call it analysis in atmospheric data simulation. The other way to do it is to look at it in a probabilistic way, wherein you have a probability distributions of your first guess, you have a probability distribution of your observations, and you want to combine those two information, and if both of them are Gaussians, you go back to your stat 101, two Gaussians, the product of two Gaussians is a Gaussian. And so you end up with this. It's exactly the same if it's linear and Gaussian. The variational and the Bayesian inference is exactly the same solution. Okay? But that's because we are assuming a Gaussian distribution in a linear case. All right. So main points, before I go on, there's a combination of information. There are two approaches that are based on linear and Gaussian cases, our analysis is very sensitive to our guess, the level of confidence we have. Okay, those are sigma naught, sigma b, and xb. All right, so keep that in mind because a lot of people don't know this. We ask Dave Adams this, and we guess this. So just to make that clear, the solution that I showed you is actually assuming also that it's unbiased, that Dave's observation is unbiased, that my model worth is unbiased. Okay, those are big assumptions that you really want to ask the data simulation if it's actually valid or not. Anyhow, so we got a scalar quantity, right? We have a solution. If you think about the whole NAM, where Jamie talked about, there are 3 domains in there, and so it's made it complicated. Now it becomes a vector and a matrix which has about 9 million points. A 9 million by 9 million, you cannot even do it in MATLAB or in a Fortran. You cannot put it in a storage. And so, but essentially it's the same thing. It's the ratio of errors of your observation model divided by the total area. Okay? All right. I'd like to point out as well this one. Letter B. Most of the time, obs are not collocated, are not the same variable as the model states. We're lucky that we have temperature observations and we want to estimate the temperature. In most cases, we don't have moisture. We have integrated quantity, total breathable water. In most cases, that grid box is so far from the observation. Okay, so there's really a problem with representativeness of thinking about the information that you have and how is it representative of that box. Okay, that is a big question which we data simulation just hand wave. In some cases we ask Dave, in some cases we ask the model, but essentially there's just limited information to do that. It's a big, you can get a PhD out of looking at the representativeness error. Anyhow, so you have more unknown states, you have less observations, and you even want to know what is X3 based on this, based on that, based on that. If it's very far, you can still get some solution to this by saying, well, this one is correlated with this is correlated with this, and so this two are, I can update this because it's very near here, and if this is correlated with this, then I can update this. That's all there is. Okay? So that correlation is based on the models, based on the sensitivity. And so if the model is wrong, forget about data simulation. All right. Okay. I added an H here because in some cases, like the TBW, it's an integrated quantity. And so you need to kind of map your observation to the model space. And imagine, we were talking about temperature before at 9 million. The state vector that we're looking at for atmospheric state, this is very basic. Temperature, UV, W, and even the surface, the 2-meter temperatures. And this is about 100 million elements. You want to solve this problem? Forget about it. There's a lot of approximations built into this. Anyhow, I'd like to just throw this out because there was a question about how we do it in Dart. What we do is just to take the column of the cube vapor and weight it by their pressure. That's our kind of expected observations that we can compare with Dave's DPW. The assumption there is that I don't consider that angle. I just want to have the single column model, and that's what we do. We can take the average of a 2.5 across the 10 kilometers, but we don't do that now. We also assume 1.5 millimeter. Some people look at it as a 2% of DPW, or I was told by Yolanda I'm going to use 5%. Okay? All right. So there are several flavors to this. 3D VAR and 4D VAR, that's our ECMWF is really leading that. An ensemble Kalman filter, the Environment Canada is doing that. A buzzword right now, is a fad right now, is to have a hybrid of both of those worlds. in our case, we're looking at atmospheric data simulation, which is really as an initial value problem. Several people have looked at this. Several speakers have shown this. That's an initial value problem. That's pretty much 10 years ago for atmospheric data, the operational center. Most of the time, ocean data simulation, for example, looks at initial states. That's a bigger problem. Land data simulation looks at the parameters and the fluxes. Right, so they have different interests. I'm interested in emissions, to find where it is. And so this is as a source, that's also a boundary condition of your model. But I would like to have this as well, that the system is actually a venue for the model to be confronted with the data. Every 6 hours or every hour you're confronted with the data. Hey, this data is coming in and the model is really wrong. They're far from each other. And so that increment gives you a lot of insights. Anyhow, for those of you who are interested, GP, in terms of data number, satellites dominates. In terms of observational impact, this is every day. You actually have this in the website, NASA GMAO. This is GMAO. ECMWF also has one. DENSEP has also one. And this is the tropics across 1 year. And the measure is moist total energy. And the negative here means it's the reduction in the forecast error of that total metric, the moist total energy. And you see that in the tropics, you have radioson, and AMSU is always there. I don't know where it goes, but GOES will be here in the northern hemisphere. So they have a bigger impact on the assimilation and the forecast scale in the tropics in this case. GPSRO is over here. Okay, it changes as well. How many times? How many? 0? 5 minutes? Okay. All right. So this is my talk, current challenges and opportunities. I view this as the same thing, challenges and opportunities. When I look at the literature, and I'm a novice of North American monsoon, thanks to Yolande and Chris for teaching me, I look at this and I said, okay, this is name, right? I Google name data simulation. What are the papers that are out there about data simulation, looking at them? But then if you think about it, it's a key activity of the name research program. Okay? Guess how many formal assimilation studies you can get. Arguably, Google is the best search engine, Google Scholar, but that's also a different matter. 1. But maybe there is some other ongoing studies out there. But the speculation here is that it's still in the research frontier. NAM is in the case, we are in a situation where we have convective systems, we have terrain, we have Gulf surges. These are research frontiers in terms of data simulations. All right, they've looked at several, two regional data simulation schemes. What they found is, yes, it can improve moisture transport, low-level jet, but then they say, okay, the difference in adding that extra radioson and extra information in the NAM region during the name experiment is actually very small compared to the difference in their systems. That means their data simulation is so different from each other that they actually have a bigger error than the impact of the soundings. Okay? These are 3D VAR methods that they're using. That was about 10 years ago. It has evolved through time now. All right. Accounting for multi-scale features. This has been talked about a lot, right? There's the temporal and the spatial scales that we need to account for. Convection is a different scale than a large scale synoptics. So remember that I told you about the errors? That's all I've got. So bear in mind, this should be correct. The error that propagates the information should be correct, and we don't even know it, right? So ensemble approaches have actually a good way to do it, because you can have it's a system that propagates errors. And this is talk about as well, reliable IC or BC, initial conditions or boundary conditions, SSTs. soil moisture. Some of these things are hard to assimilate. SSTs, for example, are always prescribed. It is a very longer time scale, and so you end up with how do I actually assimilate an average quantity, or how to update a state variable that is an annual time scale or whatever. So that's a hard problem. One thing also is precip is a very hard problem because it's non-Gaussian. There's a lot of nonlinearities in it. And so we end up with memory issues as well because you have, remember that 100 million vectors, elements? It's non-Gaussian. There's displacement errors, shift in time and space. That is hard to actually update or change. There's also this rapid update cycling. You have to have it in 1 hour. That's why RAP or ROC is actually in 1 hour. Because if you do it in 6 hours, then you need to have a spin up before the model equilibrates. Lastly, I think this is research frontier that a lot of data assimilation community, several community has looked at. There's a coupling between atmosphere and ocean, as Benjamin has told us, but there's also coupling of the assimilation of the ocean and land. So you think about this, an observation of the ocean can actually impact temperature, something like that. But it's not well understood. The interface is not well understood. So what we're doing is to do some very, very baby step process. Analysis, and ensemble simulations. These are two different frameworks. This is a model world. This is a real observation. Okay. What if you assimilate MODIS? What will it give you? What if you assimilate Dave Adams DPW? What it give you? What is the impact of that? Okay. I'd like to have this as a highlight because I think there's a lot of opportunities to do an ensemble of simulations and look at better quantifying initial condition, sensitivity of states with initial conditions. I haven't really presented this, but this is something that's very interesting. I'm not going to talk about this, but this is a framework for analysis. We're into this right now. We're trying to assess if the network of observations we have can actually impact moisture fields in Arizona. Okay. This is something I have worked with in Arizona with the hydrology department, and I think there was a mention of this yesterday on the Cosmos network, a potential for it to be deployed here. I think this is a very interesting avenue. For those of you who don't know, this is from a neutron count. So the source of neutrons is the soil, but the water has hydrogen, and the hydrogen actually absorbs that neutron. So if you have a wet soil, then you don't have a lot of neutron that goes out of that surface. And so if you can put a sensor here, you can measure the neutrons, the fast neutrons, the high energy neutrons, and that correlates to soil moisture. We've actually done an OSSI of this. Look at 3 sites of different land cover, grasslands to croplands and mixed forests. We do an ensemble. We end up with this. It's published in the paper. The bottom line is that if you simulate TPW soil moisture from Cosmos, you can actually very improve the soil moisture in NOAA. This is a NOAA model. There's a caveat to this that if the model, the NOAA, is wrong, there is actually a spikiness in the latent heat fluxes and the sensible heat. We get soil moisture correct, but the latent heat is not. So there's the caveat there. You have to look at the allocation. But we also look at a kind of a SMAP temporal timing and 1 hour timing from Cosmos, and you see that if you have every hourly observations, you actually get a very good agreement with the true value. So I end here.
Bueno, les invitamos a que se queden aquí para ¿cómo se llama? ¿Cómo lo llaman? Análisis de tiempo. Es que ellos tienen el auditorio ahora y yo me comprometí a ir a la 1:30. Ya sé, creo que nos pasamos.
No, la 1:30.
Ok. Entonces, regresamos a las 4:30.